Hi folks, today we're going to talk about how to graph rational functions. So we're just coming back from a really long break, and this is the perfect lesson to start back up again with because it helps us review all of the little parts that we found and all the characteristics of rational functions that we were so good at finding before. And now we're going to find them again, but we're also going to graph them on a coordinate grid so that we can see what the rational function looks like. So the steps for graphing any rational function always starts out with factoring all the parts. So we got to factor all the parts. You want to find the domain using the original denominator before you simplify. The reason is, if you're simplifying, you might have some common factors that cancel out. And if a factor cancels out, then a whole occurs. In order to figure out where the whole is, you set the canceled factor equal to 0. That gives you an x value. And then you can substitute that back into the reduced function to get the y value. So you get the ordered pair for the whole. You use the reduced form of the function, reduced form meaning like after you cancel out any common factors, to find all the pieces. So you find the vertical asymptote or asymptotes, because there could be more than one. You find the horizontal asymptote, if there is one, because it's possible that there is not. You find the X intercepts by setting the simplified function equal to 0 and solving for x. Remember that setting a fraction equal to 0 is the same thing as setting the numerator equal to 0, so that kind of cuts down on some of your work. You also want to find the Y-intercept by replacing x with 0 everywhere you see an x and solving for y. And finally, graph the function using information from above. Make a table for additional points if you need it. So we have one example today, and it has a lot of different things that we can find, but we know how to find them. And if we don't remember, then kind of a little blurb about finding each piece is up at the top in the steps. So the example says, identify the key features and graph the rational function. So I'm going to move this up, and we'll come back to the steps as we need them. But here is my example. Now, first step, factor all the parts. So I'm going to factor the numerator and I'm going to factor the denominator. Kind of split this with these words in the middle. So for a trinomial, there's no GCF I can take out, so I'm going to use magic numbers. I need two numbers that multiply to give me 2 times 3, which is -6, and they need to add to give me 5. Now, this is kind of interesting because the a value is 2, not 1. So what I'm going to do is out to the side, I'm going to have to factor this. And I'm going to have to use factoring by grouping. So two numbers that multiply to give me -3 and add to give me 5. Well, 6 and 1 would work, but the 6 would need to be positive and the 1 would need to be negative. So I'm going to make this term become -1x plus 6x. And then I'm going to factor by grouping. So I'm going to group these terms and these terms. I'm going to take out an x, and I'm left with 2x minus 1. Here I'm going to take out a 3, and I'm left with 2x minus 1. So one of my factors is 2x minus 1, and the other one is x plus 3. So that's how I get my factored numerator. 2x minus 1 and x plus 3. Now for the denominator, I use magic numbers also, but because a is 1, I can just write my magic numbers here as the constants for my factors. So I need two numbers that multiply to be -3 and add to be 2. Well, that would be 3 and 1, but the 1 needs to be negative. So x plus 3 and x minus 1. I notice that x plus 3 is a common factor on top and bottom, so I'm going to cancel those out, and my factored function is going to be 2x minus 1 on top and x minus 1 on the bottom. Now, the domain. I need to use the original denominator before I simplified so that I can pick out the x values that can't happen in the domain. Well, that's fine. The domain is all real numbers, except My denominator can't be 0, so x plus 3 equals 0 would give me an x value of negative 3, so I can't have negative 3. And x minus 1 equals 0 would give me an x value of 1, so x can't be 1. Okay. The wholes. Remember that after a factor cancels out, a whole occurs. So you set the canceled factor equal to 0, solve to get x, and then plug it back in to get y. So I go look at my canceled factor. My canceled factor was x plus 3. So I'm going to set x plus 3 equal to 0. X equals negative 3, so there's the x value of the whole. The y value happens when you substitute negative 3 in place of x. So 2 times negative 3 minus 1 on the top, and negative 3 minus 1 on the bottom. Well, 2 times negative 3 is negative 6, and negative 6 minus 1 more is negative 7. Negative 3 minus 1 more is negative 4. And 7 over 4 doesn't simplify, but a negative over a negative becomes a positive, so this y value is 7/4. Just under 8/4, which would be exactly 2. Okay. So let's find the vertical asymptote. The vertical asymptote comes from the denominator of the simplified function. So if x minus 1 equals 0, x has to be equal to 1. There's my vertical asymptote. It also should match up that your domain values that you have to take out of the domain, so negative 3 and 1, that should match up with the whole and the vertical asymptote. The horizontal asymptote I determine based on the degrees of my numerator and denominator. My numerator is degree 1, my denominator is degree 1. Since they're the same degree, then I take the coefficients of those x terms, and that's my horizontal asymptote. So my horizontal asymptote is the coefficient of 2x, which is 2, and the coefficient of x, which is 1, and 2 over 1 is just 2. So there's the horizontal asymptote. I'm going to skip the range for right now. We'll come back to it because it's kind of new. I'm going to go to the x-intercept and the y-intercept, remembering that the x-intercept is the x value when y is 0. So I'm going to set the function equal to 0. So x-intercept, set the simplified function equal to 0 and solve for x. So the numerator is what we set equal to 0, because the numerator of a fraction, if that's 0, then the function is 0. So my numerator is 2x minus 1. If I set 2x minus 1 equal to 0, 2x equals 1, and x equals 1/2. So there's the x-intercept. The y-intercept comes from replacing x with 0 and solving for y. So I'm going to take f of 0. I'm going to set it equal to 2 times 0 minus 1 over 0 minus 1. 2 times 0 is 0. 0 minus 1 is negative 1. 0 minus 1 is negative 1. And negative 1 over negative 1 is simply a 1. So this is 0, 1. So I have all the pieces except for the range right now. And I'm going to skip that because I want to talk about the graph before I find the range. I think it'll make a little bit more sense. So I'm going to graph all the pieces. I have a whole at the order pair negative 3, 7/4. So negative 1, 2, 3. And I'm going up about 1 3/4. So about right here, there's a hole right there. There's a vertical asymptote at x equals 1. So vertical, going through an x value of 1 right there. There's a horizontal asymptote at y equals 2. So going through a y value of 2. The x-intercept is at 1/2, 0. So 1/2, 0. The y-intercept is at 0, 1. That's right here. And that's what I know about my graph so far. And that's enough to graph at least part of this hyperbola. So I know that it looks like this, goes through the hole, goes through the y-axis, goes through the x-axis, and then it comes down and it approaches that asymptote. But I don't know anything about this side over here. Now there's no holes and it's not going through an axis over here, so I sort of know what it looks like, but perhaps I need to make a table, and I'll do that in a moment. However, I do want to talk about the range here. The range is the set of all y values in your function. So from the bottom to the top. Well, the bottom has an arrow. So it extends from negative infinity all the way up, 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 up. However, there's no y value at the hole, and there's no y value at the asymptote. So I'm going to go get my highlighter. The range is all real numbers except y can't equal the y value for the horizontal asymptote and the y value for the hole. I have to take those out of the range because there's no y value there. So keep that in mind. And it turns out that the same thing's happening with the domain. The domain is all real numbers except the x values for the hole, here, and the vertical asymptote, here. So the holes and the asymptotes affect directly the domain and the range. Now, the last thing that we need to do is we need to figure out where the hyperbola, this part of the hyperbola is. So the x values that I'm interested in are maybe like 2 and 3. So I'm going to make a table. I need the y value when x is 2 and the y value when x is 3. Maybe that will help me out a little bit. So I'm just going to substitute 2 for x, and I'm going to solve. So 2 times 2 is 4. 4 minus 1 is 3. And 2 minus 1 is 1. So that y value here is just 3 over 1, or 3. So the ordered pair is 2, 3. 2, 1, 2, 3. Perfect. There's a point on the hyperbola. Next x value that I need to find a y value for is 3. I'm going to substitute 3 in place of x everywhere I see it. So 2 times 3 is 6. 6 minus 1 is 5. And 3 minus 1 is 2. So 5 halves. So I'm going to go over to an x value of 3, and I'm going to go up 1, 2, 3, 4, 5 halves. And now I kind of have an idea of what my hyperbola looks like on this side of the vertical asymptote. So it kind of comes down like this. So in our notes today, we have reviewed how to find the domain, the holes, the vertical asymptote, the horizontal asymptote, the x and y intercepts. We've reviewed factoring a little bit. We've learned how to write the range of a rational function. So you need to take out the y values for the asymptote and for the hole. And then we've also learned how to put it all together on a graph and make sense of what all of these pieces look like.